Alright, hello everybody. So today we're talking about the dot product. So our question here is, how do we multiply two vectors? Right, so we know how to multiply numbers, but we don't necessarily know how to multiply vectors. Remember, vectors are things, so scalars are just numbers. They just have magnitude, but vectors have both magnitude and direction. So we want to figure out how to, we know how to just multiply magnitudes, but we don't know what needs to happen to the directions. So we need to figure out some sense of multiplication here. So I'll say one of the ways to multiply vectors is the dot product. The other way is the cross product. Right. So we've got two ways to multiply vectors. One of them is the dot product, and the other one is the cross product. So we're not going to talk about the cross product today, but we do want to talk about the dot product. So let me get a different color here. So let's figure out what the dot product is. So definition, if A equals A1, A2, A3, and B equals B1, B2, B3, then the dot product of A and B is the number A dot B, so A dot B, so that's what we call the dot product. So this given by, so we're going to say that A dot B equals A1 B1 plus A2 B2 plus A3 B3. Okay. Right. So we're saying the way that we take the dot product is just multiplying together the components. So this is the x component in both of them. We multiply together the x components. We add when we multiply together the y components, and we add when we multiply together the z components of each of these vectors. Right. So if we add all of this together, that's what we call the dot product. Okay. And the thing to notice here is we're multiplying together numbers and we're adding together these numbers. So the output of this is actually a number, not a vector. Right, so I'll say here, since A dot B is a number, we sometimes call the dot product so we'll sometimes call it the scalar product or inner product. Right. So if you take any other math classes, you might see scalar product or inner product used instead of dot product, but they mean the same thing. Okay, so our first thing here is an example. So let's say here, example number 1. It's going to say find A dot B. Okay, and for part A, it's going to say A equals, so remember this is the representation, so it's going to have x component -1, y component 7, and z component of 4. And we're going to say that B equals, let's say that this is going to be, I have to read what it says there, yeah. Okay, 6, the y component is 2, and the z component is -1/2. Right, so these are our two vectors, and we're trying to find the dot product of the two vectors. So as I said here, A dotted with B is going to be, so you multiply together the x components, so -1 times 6, plus you multiply together the y components, 7 times 2, plus you multiply together the z components, 4 times -1/2. Right, and the dot product is as simple as that. You just multiply together the components, that gives you the answer. So if we just multiply everything together, we get -6 plus 14 minus 2. Right, so 14 minus 8, that's going to give us a total of 6. That'd be our answer here. So that's the dot product. Let's do one more example though, or one more case in this example. So part B is going to say that A equals I hat plus 2j hat plus, or sorry, minus 3k hat. And let's say that B equals 2j hat minus k hat. Okay. And the thing to notice here is that when I wrote down B, we don't have an I component, so this is the same thing as saying 0 times I plus 2 times j minus 1 times k. Right? So these are the same things. So here it just doesn't have an I component, so the coefficient for I is 0. Okay, and now we just need to find A dot B. So let me actually use a different color here. So here our A dot B is going to be equal to, so we multiply together the I components, the j components, and the k components, right? So here the I component is 1 and 0, so we're going to have 1 times 0. We multiply together the j's, so 2 times 2. And then we multiply together the k's. We've got minus 3 times minus 1. Right, so we just add together all of these things. So this first one cancels out, the second one is 4, and the third one is 4. So our answer here, third one is 3. Negative 3 times -1 is positive 3. So our answer here is 7. So that's the dot product of the two vectors. Okay. The next thing to write down here, let me just flip to the other side. So the next thing to write down, I'm just going to write down some nice properties. So I'll say here, some nice properties. And for number 1, I'm going to say if you take the dot product of a vector with itself, you can try to think about what happens there. Well, you're multiplying each of the components by itself, so actually what you're going to get is the length of A squared. This is what you're going to get. Okay? The second property here is going to be if you have A dotted with B, then that's going to be the same thing as B dotted with A, because if you remember our formula, we didn't care which one was the first vector and which one was the second vector. So we can say that it doesn't matter which order you do the dot product in. Okay, the third property here is going to say that if you have some constant times A, and you're doing the dot product with B, and that's going to be the same thing as C times the dot product of A with B. And that's going to be the same thing as A with, and then the dot product with C times B. Right? So you can move that constant around, and it doesn't matter where you put it. Okay. And now our fourth and final property here is going to say if you have, I should probably use, so I'm using the numbers actually for the examples. I should maybe use Roman numerals here instead of numbers, so we'll go ahead and do that. But this is property 1, 2, 3, and 4. Right, so property number 4 is going to say that 0 dotted with A. Right, so this is the 0 vector, meaning it's just the vector with 0 in all of its entries. And if you think about the formula with what happens whenever you dot that with A, you can think about what the answer should be. And of course the answer here is going to be the number 0, right? So the output is always a number, and the number here is going to be 0. Okay. Let me use a different color. So let's say if we place the initial points of A and B at the origin, and let theta be the angle between A and B, where, so there's two choices for the angles between two vectors, but you can always pick the angle that's less than 180 degrees. So I'll say here where 0 is less than or equal to theta is less than or equal to pi, because pi is the same thing as 180 degrees, so you can just choose the smaller angle. So the thing we get here is that A dotted with B is actually equal to the size of A times the size of B times the cosine of theta. Sorry, I should actually use a different color here. Let me just rewrite that, because this is important. So the important formula here is that A dotted with B equals the size of A times the size of B times cosine theta, or cosine theta equals A dot B over size of A times size of B. Right, so these are both the same formula. I've just rearranged this formula. I've divided by these numbers on both sides to get that formula. Right, so these are both the same, but that's what we get. And the setup to this is, let me just draw a small picture here. So this is the x direction, the y direction, and the z direction. And let's say we have our two vectors here and here. Let's say that this is A and this is our vector B. Then the angle between them is theta, right? So we're taking theta to be the angle between the two vectors, and we're saying that the dot product of A and B is actually equal to the multiplication of their two lengths times the cosine of theta. Right, so that's how the dot product has to do, what the relation is with this angle, right? So here, as I said, theta is the angle between them, and let's do an example here. So example number 2 is going to say if A and B have lengths 4 and 6, and the angle between them is pi over 3. Find A dot B. Right. So this is the problem here. A and B have lengths 4 and 6 respectively. The angle between them is pi over 3, which is the same thing as 60 degrees. We need to find A dot B. Okay, so we just use the formula. So it says in the formula that A dotted with B is equal to the length of A, which we said was 4, times the length of B, which we said was 6, times the cosine of, times the cosine of theta, which is the cosine of pi over 3. Right. So notice here, I'll still use this symbol for multiplication, but if you're multiplying two numbers, that's just what you normally do. Here, whenever you see this dot between two vectors, that's when we're using the dot product. But if you're using this symbol between two numbers, it just means regular multiplication. Okay, so this is just 4 times 6 times cosine of 60 degrees. And once again, to figure out the cosine of 60 degrees, we again use our unit circle. So this is our pi over 6, our pi over 4, and our pi over 3. We again write 1, 2, 3, then 3, 2, 1. Take the square root of everything, and then just divide everything by 2. And then you make everything into a point. Right? So once again, that's how to find the unit circle. And we're trying to find the cosine of pi over 3, so it's just the x-coordinate of pi over 3, which is going to be a half. So the answer there is a half. So we've got 4 times 6 times 1/2, which is 4 times 3, which is 12. So that'll be our answer. Okay. So let me go ahead and erase this. All right, so we just use that to figure out the cosine of pi over 3. And that's what I'm always doing in my head whenever I'm trying to figure out the cosine of some angle or the sine of some angle. So let's do example number 3, which is going to say, find the angles, find the angle between the vectors A equals 1, -2, -2, and B equals 6, 3, 2. Okay, so these are our two vectors, and we're trying to find the angle between them, and as is the name of the section, we probably want to use the dot product. So notice we can figure out what the dot product is. We can figure out what the length of a vector is. Remember, we had a formula for that. So we can figure out this, this, and this, but we need to figure out what theta is equal to. So we don't know this side of the equation, but we know all the stuff on this side of the equation. Or at least we can figure out all the stuff on this side of the equation. So we're going to figure out these three things: A dot B, length of A, and length of B. Okay. So I'll say here, let me write it in a different color. So our strategy that we're using is to find A dot B, length of A, and length of B then use cosine theta equals A dot B over length of A times length of B. Right? So we just got to find these three things, and then we can use our formula to figure out theta. So our first thing first thing I'll say here, the first thing I'll try to find is length of A. So length of A. And remember, in order to find the length of a vector, we take the square root of the sum of each of the entries squared, right? So we square the first entry, plus we square the second entry, plus we square the third entry. Right? So that's how we find the length of A. So we just compute what this is. This is 1 plus 4 plus 4. Square root of 9. Square root of 9 is 3. So that's our answer there. Then our length of B is going to be equal to, so we just do the same thing for B. Right, so the x component was 6. We square it, plus we square the y component, plus we square the z component. Right, so that's what we get here. So 6 squared, that's 36, plus 9, plus 4. So thinking what that would be in my head, so 36 plus 9, that's 45. Square root of 45 plus 4. So the square root of 49, so you think what times itself gives you 49? The answer is 7, because 7 times 7 is 49. Okay, so we figured out length of A and length of B. And now the last thing we need to figure out is A dot B. So A dot B, remember our formula, we just multiply together the components and add them. So we multiply together the x components, so 1 times 6, plus we multiply together the y components, -2 times 3, plus we multiply together the z components, -2 times 2. And then we just add everything up, right? So that's going to be 6 minus 6 minus 4. So we're going to get -4. Right, so A dot B gave us -4. Okay, so we figured out all three of those things, and now we can use this formula right here. So we know that cosine theta, or I should say here, yes, so cosine theta equals, so A dot B we said was -4 over, we said we multiplied length of A times length of B, so 21, right? So 3 times 7, that's 21. Just using that formula. And now we need to figure out theta. So if we know cosine of theta is equal to this, the way we figure out theta is just by taking cosine inverse on both sides. So cosine inverse of cosine, that just gives us back the angle. But then you're left with cosine inverse on the right side. So you're going to get theta equals cosine inverse of -4 over 21. Right, so I took cosine inverse of this side, got theta, cosine inverse of that side, that's what you get. And then you just plug this into the calculator. Remember, you need to keep your calculator in radian mode, because if your calculator is not in radian mode, you're going to get an answer in degrees. And all the math that we do is always going to be in radian mode. So you want to make sure your calculator is in radian mode. And once you do that, you're going to get approximately 1.76 radians. Right, you don't need to write the word radians, but your answer here is 1.76, and I just wrote radians so that we can remember that this is actually an angle, right? Okay, so let me write down the next thing here. Let me erase this. Okay, so we'll say two non-zero vectors A and B are, we'll say, perpendicular or orthogonal. That's not what I meant to write. Orthogonal. Right, so we use both words, either perpendicular or orthogonal. They both mean the same thing. If the angle between A and B is pi over 2. And remember that pi over 2 radians is the same thing as 90 degrees, right? So if we were to draw a right angle that's 90 degrees, it has two arrows that look like this. They're separated by 90 degrees, so it's just, this is the shape that it makes, right? So the perpendicular symbol is actually this shape, so this line is perpendicular to this other line because it exactly intersects it at this 90-degree angle on both sides, right? So that's what two perpendicular vectors are. They're just two vectors that have an angle of 90 degrees between them. Okay. So I'll say here, theorem 1. So we're going to have a theorem here. Two vectors are orthogonal, or sorry, two vectors, what I meant to write here, two vectors A and B are orthogonal if and only if A dot B equals 0. Okay. Whenever I write if and only if, I mean if the first condition holds, then the second condition holds. And the only if part means if the second condition holds, then the first condition holds. Right? So what this is saying is if they're orthogonal, then the dot product is 0. And the other direction is saying if the dot product is 0, then the two vectors are either perpendicular or orthogonal. They both mean the same thing. So you can think about, so I'll say here, try, prove theorem 1. Right, so I encourage you to think about why this has to be true. So you think about if you have the first condition, why does the second condition hold? And if you have the second condition, why does the first condition hold? Just using that formula that we had for the dot product. So I encourage you to think about that. But moving on from that, we'll say here, right, so perpendicular lines means just two lines that meet at 90 degrees, and parallel lines are two lines that run like this, right? They're parallel to each other, meaning they never intersect, right? So we wrote down what orthogonal means, and I'll say two vectors, so vector A and vector B are parallel if and only if they are scalar multiples. Right, so thinking about why this has to be true, if we draw two vectors that are the exact same direction and length, so let me draw the same vector but over here, that actually looks a bit longer, but these two vectors are both the same direction and the same length, or sorry, that's not what I meant to say. They're the same direction, so if they're parallel, they're in the same direction, that's what I meant to say. So just two vectors that are in the same direction, they're parallel. Now, what we can say is that one is just the scalar multiple of the other because you can say, well, you can always just move this vector around, and if you just move this vector on top of the other one, you can see, well, if you just make this bigger, it's the same thing as that vector, right? So if two vectors are scalar multiples of each other, that just means that they're parallel. The two things mean the same, right? They're just equivalent ways of stating this, right? So if we've got two parallel vectors, that's the same thing as saying that they're scalar multiples. Okay. So we actually want to be able to check this condition. So we want to be able to check whether two vectors are indeed parallel. Meaning they have the same direction. Either the same or opposite directions, because that still means that they are on the same line. Okay. So let's say here A equals the vector 3, 12, negative 6, and B equals the vector negative 2, negative 8, comma 4. And we want to show that they're parallel, so are parallel. Right, so we're trying to show that these two vectors are parallel. And now we may ask, how do we do that? So we said they're parallel means the same thing that as if they're scalar multiples of each other. So if I can multiply one vector by a number to get the other vector, then they're parallel. Okay. So what that means is, so let me say to check. What we're going to check is that the first component times some number equals the first component of the second vector. Right? So 3 times whatever we're scaling this by equals the x component of the second vector. Same thing, 12 times whatever we're scaling it by should be the y component of the second vector, and negative 6 times whatever we're scaling this by should be equal to 4. So if they are indeed parallel, then we're multiplying this vector by a constant c to get to that vector, meaning 3 times c is negative 2, 12 times c is negative 8, negative 6 times c is 4. Right? So if they are parallel, then this is true. So we just need to solve each equation to figure out what c is equal to. So if we solve the first equation, then c equals negative 2/3. If we solve the second equation, we would also get c equals negative 2/3. And if we solve the third equation, we would also get c equals negative 2/3. So what this is saying is, so negative 2/3 times the vector A equals the vector B. And you can check that. If you multiply this vector by negative 2/3, you get back to the second vector, right? So this check actually shows that they're scalar multiples, meaning this means A and B are parallel. Right, so that's how you check that two vectors are parallel. You just check, you multiply some constant, the same constant, by each of the coordinates, and you see whether that works out to get to the second vector, if they are actually the same constant. Okay. So let's say the next example, I think this is example number 4, I might have gotten off with my numbering, is to show that 3i minus 2j plus k and 2j plus 4k are orthogonal. Remember, so orthogonal means perpendicular, and we said they're orthogonal if and only if the dot product is 0. So if we compute the dot product and it's not 0, then they're not orthogonal. If we compute the dot product and it is 0, then they are orthogonal. So all we have to do is compute that dot product. So we just take the dot product. So 3i minus 2j plus k. And then we're taking the dot product with, remember this is 0 times I plus 2 times j plus 4 times k. Right, so since this one doesn't have an I component, the coefficient of I is 0. So we take the dot product, meaning we multiply together the I entries, the j entries, and the k entries. So if we do that, we're going to get 3 times 0 minus 2 times 2 plus 1 times 4. Right, so I just multiplied 3 times 0, negative 2 times 2, and 1 times 4. If you multiply all those things together, you're going to get 4 minus 4, which is indeed 0. Right, so since the dot product is 0, that means that they're orthogonal. So that's the way you check that. Okay. So the next thing to talk about is actually going to be projections. Okay. So let's talk about projections. Okay. So let's say here we've got a point. Let's call this point P. Let's say we've got a point up here. Let's call this point R. And let's say we have a point here. Let's call this point Q. Okay. And actually, sorry, let me draw this a little bit lower. So we've got P here and R here. Okay. So we've got a vector from P to Q. Let me use a different color. I'll use this color. So we've got a vector from P to Q, and we've got a vector from P to R. Let's call this vector B, and this vector A. And we're going to look at projecting B onto A. So we have to look at what that exactly means. So let me draw another picture here. So I'm going to try to redraw the same picture. So this is P, this is Q, and this is R. And remember we had our vectors B, and we had our vector A. Right. So the way that we project one vector onto the other vector is we can think of shining a light. Let's think of shining a light. Let me try to draw a flashlight. Right, so you can think of this as some light that's shining at this point R, and we're shining a light from this point R down to this point here. Let's call this point S. Right, so we're shining a light from here onto this vector, and we're seeing what the projection is going to be, or in other words, the shadow that this vector casts onto this vector. So what happens is you're going to shine this light down. We're going to get a right angle here, and this is going to be the projected vector. Right? So this vector right here that I've drawn in red is going to be the result of the projection, right? So you think of a light shining here, and you just project one vector onto the other vector. So let me write down in words exactly what we just did. So I'll say here that PS, the vector from P to S, and I'll say this is a vector, is called the vector projection of B onto A. Right? So the vector projection of B onto A, that's what we did there. We just shown that, we just shown a light from here down to here, and the shadow that it casted, that was the projection. And we'll denote this, denoted, so this is the projection of B onto A. So that's the way we denote it. We've got a subscript A, and we're taking the projection of B onto A. Okay. And as I said in words here, we can think of this as the shadow that B casts onto A. Okay. Now, the next thing to talk about here, let me, I guess, write this here, is the sign length meaning it could be plus or minus, right? So either could be positive or negative, of projection onto A of B. So we're just looking at the length of this vector. We're saying the length of the red vector could be positive or negative, but the length of this projected vector, so the vector I drew here in red is projection onto A of B, right? So the length of this projected vector is called the component of B along A. So I'll underline that. Or scalar projection of B onto A. And I'll say here that this signed length is called, or denoted, by comp sub A of B, right? So the length of this projection vector, we're saying, is this number right here. So what I wrote down here is that the vector, so I'll say here that projection onto A of B is a vector, right? So this thing here, that was the vector, and the length of this vector is this. So that's actually a number, right? The length of a vector is a number. So I'll say here that comp sub A of B, that's a scalar, right? Remember, when I say scalar, I mean the same thing as if I say number, right? So it's just a number. Okay. So, and I'll give you a couple formulas here so that we can actually work with these things. Okay. So, formulas. So the formulas are going to say, so the way that we're going to find the length of this projection vector which we denote by this, is that we're going to say that this is A dot B, right? So this is the dot product over the size of A. Right, so if we take this number, that's actually the length of the projected vector. So I'll say that this is scalar projection, as I wrote over there. Okay. And the second formula here is that proj A of B is going to be equal to A dot B over the size of A. So the same thing here, which is the length of the vector times, well, the length of the vector is going to be, this vector is going to be whatever its length is times the unit vector in that direction. And the unit vector in the direction of A would just be A over the size of A, right? We make a vector into a unit vector by dividing by its size. So if we multiply this out, we're going to get that this is A dot B over size of A squared times the vector A. And this is vector projection. Okay, so we get these two formulas. I kind of wish I hadn't written them in the same color here, but we get these two formulas. So we have the formula at the top here. That's the way you find the scalar, and the way you find the vector is this formula down here. Okay. And the next thing I'll write here is the next example. So example number 5, I think it is. This is the last one here. Is find the scalar and vector and vector projections of B equals 6, 3, and 2 onto A equals 1, 2, and negative 2. Right, so the first thing we need to identify is the fact that this is being projected onto A. So B is being projected onto A. So A is the subscript, and B is this part here. Right, so it's the same as the formula that I wrote up there. Okay. So the first thing, so we need to figure out both of these things. And the first thing that we need to figure out for both of these formulas is the size of A, right? So both of these formulas involve the size of A. So we need to figure out the size of A. So I'll write here the size of A equals, remember our formula for the size of A was we take the square root, and then we just take each of its components and square it. So 1 squared plus 2 squared plus negative 2 squared. Right? If we're plugging something into a formula, we just add parentheses around the negative number because in this case, it actually becomes positive. So this is what we get. We add all the numbers together, we get the square root of 9, which is 3. So the length of A is 3. Okay. And then the next thing we need to figure out for the formulas is A dot B. Remember, so we need to just use our formula we had for that. And remember, it didn't matter whether we chose B to be the first vector or A to be the first vector. So I'll do 6 times 1 plus 3 times 2 plus 2 times negative 2. And if we multiply all these numbers together, we get 6 plus 6 minus 4. So that's going to be 8. Oh, wait. Ooh, sorry. I missed. Oh, yes. Okay. Sorry. this was supposed to be a negative 2. That's where I messed this up. So this was negative 2 squared, and this would actually be a negative 2, right? So it doesn't change that much. It's just now for this formula, what we get here is going to be 6 minus 6 minus 4, which is equal to negative 4, right? So I just missed that minus sign in that problem, but that's going to be the answer here. Okay. So the first thing we need to figure out is going to be the scalar projection. So the first thing is the scalar projection, which we said was comp A with B, which we just used the formula. It's the dot product over the size, right? So the dot product was negative 4 over the size, which we said was 3, right? So this is our answer. So this is the scalar projection. It's just that number. Okay. And the next thing is going to be the vector projection. So we can write proj A of B, which is equal to, so we just use this formula here. So it's A dot B over size of A squared times A, the vector A. So we just got to write down what all this is. So A dot B we said was negative 4 over the size of A, 3 squared, times this, so times the vector A. So 1, negative 2, negative 2. So we just multiply this out. That's negative 4 over 9, and we distribute. So if we distribute negative 4 over 9, right, so this is negative 4 over 9, because 3 squared is 9. So if we distribute negative 4 over 9 into here, we're going to get negative 4 over 9. And then this times negative 2, that's going to be positive 8 over 9. And the third component, negative 2 times this, is also going to be positive 8 over 9. And that would be our answer. Sorry, let me clean this up a little bit. Okay, that would be our answer. So that's the vector projection, and our scalar projection was negative 4 over 3.